stability. So now let's no. Let's now think about convolution in terms of a process that we should be pretty comfortable with. And that is the response of a low-pass filter. And let's just say that that low-pass filter is now filtering a pulse waveform. If somebody starts talking about a low-pass filter, what are you seeing now mentally? Could be seeing a frequency graph, a Bode plot, which is flat for a while and then it rolls off. If I said, give me a circuit that will realize a low-pass filter, what kind of a circuit do you now see? There's quite a few different ways of thinking of this. The most maybe direct is an RC filter. Maybe you think of an RL filter, an inductor and resistor. But inductors are heavy, so we'll just stick with capacitors. Didn't want to carry inductors around, but we might like to carry some capacitors around. So an RC circuit could act. What's the transfer function? You're going to need to be able to find some transfer functions of circuits. Here's our low-pass filter, which we might just say is our system. Describing that another way, we could write it as a transfer function. So I know that that's this S times R, where you know it's going to end up with this 1 over S tau plus 1, where tau is the time constant, and that's equal to RC. Or you might like to see it in pole zero form, which will allow you then to more directly inverse Laplace transform that. You now have h of s. If you factor out the RC from that first term, you could really put that RC factor up in the numerator, and you have a 1 over RC, and then downstairs you have an S plus 1 over RC. That's our system, and now let's say that we want to excite that system or pass through that system an input, and we said that that input was going to be a pulse. And let's just say that that pulse has an amplitude of 1 and a time duration of 3 units of time. And now we would like to have an intuitive feel or a qualitative feel as to what's going to happen when I push this pulse through a low-pass filter. That's what you need to start developing. Here, if I now applied that pulse to these terminals at the input side of this system, what am I going to see at the output? So now your answer is it depends, right? depends on your low-pass filter. It depends on the R and the C value. Depends on the frequency response of this system, of this circuit. Let's look at a couple of scenarios. And actually, let's start getting used to looking at this in many different domains. In the frequency domain, let's say the Bode plot magnitude could look like one of two pictures. It could look something like this, where I'll say that this is omega sub s, where the s stands for the system is slow or the bandwidth is small, and this omega sub s is that break frequency, which is 1 over, let's say, R sub s, C sub s, or it's 1 over tau sub s. Let's say that's a Bode plot of a low-pass filter that doesn't have a very big bandwidth. And we could compare that with a system that has a cutoff frequency omega sub f, where the f might stand for fast, or maybe it has a large bandwidth. And omega sub f now depends on two different parameter values, R and C. Let's just call those R sub f and C sub f, or this is now 1 over tau sub f. And how that pulse gets pushed through that system depends on, or what the output looks like, depends on what this break frequency or cutoff frequency is. The response is going to be different for a low-pass filter that has a large bandwidth versus one that has a small bandwidth. Now, if we didn't like to think in the frequency domain, maybe we could also talk about these two systems in the time domain. Meaning now, let's think about the impulse response of this system that has a time constant of tau sub s. Let me say that this is now h sub s of t. And what does that look like? If this was now the system, now I have 1 over tau sub s over s plus 1 over tau sub s. This now, as a system in the time domain, has what kind of a impulse response? It has an exponential decay, doesn't it? And it's going to be scaled by this 1 over RC. And the exponential decay is influenced by this time constant, RC. Or you could say this is some scaling factor. It's now e to the minus scaling factor t, and in this case that scaling factor is 1 over RC. If we now have a small t sub s, we just said that we're starting here, 1 over t sub s, and then we decay exponentially, and this is now this, bless you, e to the minus t over tau sub s. And we could compare that with what would happen for a higher bandwidth low-pass filter. And what does this one look like? Structurally, it's exactly the same, isn't it? It's just now that tau sub f is Omega sub s, that was small, wasn't it? Omega sub f is big. Tau sub f and tau sub f and tau sub s are related in what way? Tau sub f is smaller. It's fast, isn't it? The time constant for this system is fast. This is small. So if this is small, when we divide it into 1, it's going to be much higher, isn't it? So our y-intercept is much higher here when it's 1 over tau sub f than what it was in the slower system. We now have, let's say, 1 over tau sub f, and this is now this e to the minus t over tau sub f shape, which is much sharper, and now this one looks more like an impulse response than the other one, doesn't it? So our system now, the fast system, looks more like an impulse response in terms of its impulse response versus the slow one. And that's going to influence what the output response looks like. Now if we look at the output response, again in the time domain, what do we expect to see over here for the output? This is now V sub O of t. We push a pulse through this, and now if you're thinking convolution, we need to convolve that pulse with this impulse response, and that will give us our output. If you wanted to just think in terms of behavior of this system, if I now applied a step to this system and it's slow, what's going to happen? It's just going to gradually have this RC shape, isn't it? And then I only have a finite duration pulse. I'm going to turn it off. It'll be charged up, and then I'll just turn things off and it'll start to discharge. And it's going to discharge pretty slow because it's a slow system. The output response then up here is going to look, whoops, and then it'll hit 3, and then it just starts to decay. And that doesn't look all that much like the original input, does it? But the more our system's impulse response, the more it looks like a true impulse function, the more the output is going to look like the input. That's the point I'm trying to make. Now if we go down here, and if we look at the same question, this is now V sub O of t. What's going to happen to this output? Now it's going to charge up really fast, isn't it, that capacitor? And the output voltage is going to reach its final value quite quickly because it's a fast system. And then we'll get to 3, and it will discharge very fast. And now that output looks almost like the input, doesn't it? And it all depends on how close this impulse response looks like an impulse function itself. The more that impulse response of your circuit or system looks like a true impulse, the more your output is going to resemble your input. That's what I'm trying to say qualitatively. If you now looked at these two systems in the S-plane, what are we looking at? If I now had, let's say this is the S-plane for the slow system, and this is the S-plane for the fast system. And I'm now sketching X's and O's associated with that system. Did I have any zeros? I had no finite zeros in that capital H of S, but I did have one pole in each one. Where am I going to put those single X's? So now I have a pole, let's say right here, which is at minus 1 over tau sub S, and we said tau sub S was big, so that 1 over tau sub S is not going to be very far into the left half plane. And this one is quite a ways. This slow system then says that the pole is close to the j omega axis. And here, the pole for the fast system is further away. From the j omega axis. And that's another frequency domain picture of what's going on. Meaning I could have given you this, and then you could sketch the Bode plot. And you could say, oh, I'm flat for a while, and then I break at this small frequency. Or I'm flat for quite a while, and then I break at this frequency, and then I start going down. And those two Bode plots could be consistent with this S-plane plot or picture. This, I'm not sure how much of a test question this is like. The question, I think, was, is this a test question? I want you to have this insight sitting there ready to be activated when you're asked other questions on the exam, but this might give you a way of sort of checking your work or thinking through the solution. You're going, oh, what should I be seeing at the output? Let's now look at using that information for the following. Let's do a convolution problem. Suppose now, and what's the convolution integral? Definition. So let's say that we have, it's something of something of something, isn't it? So let's let our somethings be f's. Let's say that we have two waveforms. One will be f sub 1 and the other one will be f sub 2, and we want to convolve two waveforms. That's really what we were doing up here, qualitatively. We were convolving this with that pulse that was 1 for 3 seconds and then off, and that's what produced this. So let's do that numerically or analytically. But now we have this f sub 1, and I'm not sure what I'm going to always be using for variables. Let's let our variable of integration be lambda. Then we have to take the other waveform and we need to flip it. And then we'll slide it through f sub 1. To do that then, its argument is t minus lambda, and we integrate over all lambda. We'll be given two waveforms, an f sub 1 and an f sub 2. And this formula will allow us to compute their convolution, where we could just do this to do it. But for an intuitive sense, f sub 1 might be an impulse response of a wave of a system, and f sub 2 might be the input. Then y is indeed the output of that combination of that input being applied to the circuit that has an impulse response f sub 1. Let's pick some f's. Let's say here is f sub 1 of t. We'll start it at 1, and then we will just let it be exponential. And it's now e to the minus 2t. Suppose that f sub 2 is more like an input waveform, and let's just do what we had just done. Suppose that we let it be a pulse, and now let's let that pulse be of height 2 for 3 units of time. And now we want to convolve these two waveforms. And just looking at those, what I would like for you to be able to do maybe on the exam is quickly sketch the answer. And then you can start crunching through the numbers and seeing if my initial thought of an answer is somewhat close. Now, how are we going to determine whether a pulse of duration 3 units of time, how is that related to this system that we could say is an impulse? What are we wanting to come to understand about this system? We need its time constant, don't we? Let's now look at the time constant of f sub 1. What is the time constant? Well, that's when the exponential factor is equal to 1. So that's the value of time, t, and we'll say that's equal to tau, when that 2 tau is equal to 1. So it's the value of time when that exponent is equal to 1, or our time constant now is 1/2. What does this time constant of 1/2 tell us? If we now applied a step to a system, to a circuit that had this as its impulse response, how long will it take before we sort of get to where we wanted to go? 5 time constants. In this case, it's going to take us 5 of these, 5 halves, 5/2. That's 2.5 seconds. So we're actually going to reach our steady state before the pulse stops. Is that making sense? So we will have reached our final value effectively before the pulse turns off. So we'll be coming up here and then we'll shut down. It's not going to be, oh, I'm barely there. Then it would look more like a triangle if our time constant was, let's say, 10. Then we wouldn't get hardly anywhere before we would turn the pulse off, and we wouldn't have that capacitor charged up at all, hardly. Let's now look at convolving these. Now, I've already given the answer away a little bit, but we need to flip and slide one of these. So I'm going to be saying that a lot. One of these waveforms needs to be flipped and slid. Which of these do we want to, and when I say flip, I'm meaning we want to flip it relative to this vertical line at t equals 0. So it's probably easier to flip and slide that more trivial functional form, isn't it? If I flip that, it's going to look pretty clean still, and then when I slide it, I'm just going to slide it from -infinity all the way up to +infinity. That's what I mean by the slide part. Let's now flip and slide f sub 2, and we may need to flip and slide in here as warm as it is, right? Are we going to draw the answer first? Do you want to draw the answer first? What do you think is going to happen? We just said, didn't we? We said that by 2.5 seconds, this guy is going to be charged up. Now, the final value of this is going to be influenced by this guy and that guy. But let's say that we don't know what that is, but this is our final value. Then the output would be something like that, where it may look a little bit cleaner than that. It may actually build up quicker than that. That's why I didn't really want to sketch it, because I knew my sketch wouldn't be very accurate. So it's effectively flat from 2.5 to 3, correct. And it's probably effectively flat in our sketching accuracy at 4 time constants, so at 2. So it's pretty much flat for an entire second, and then it rolls off, because we're within 2% of our final value after 4 time constants. And by sketching, I can't draw a 2% accuracy with paper and pencil. Let's see. We'll figure that one out. Okay? So let's go ahead and now see if we can analytically compute this output response. And to do this flipping and sliding, let me just do it in 3 stages. I'm starting with, well, I have f sub 1 of lambda that I need in my argument of my integral, convolution integral, and that's just going to look exactly like f sub 1 of t, except now the t is replaced with lambda. So this is now e to the minus 2 lambda. That's my f sub 1 of lambda. If I flip f sub 2 with respect to lambda, if I now assume f sub 2 of lambda and now I flip it, what's it going to look like? If this is now f sub 2 of minus lambda, what's its picture look like? Now I just rotate it across the vertical axis. It's now 2 units high and 3 units wide. So my drawing accuracy is pretty poor. Looks taller than it is wide, but it's supposed to be the other way around. Okay? So I've labeled it. That's the key. Okay? Now I want to slide it, or allow it to be slid, and that means that I need to introduce this variable parameter t. And I'm going to, for sketching purposes, go ahead and let that t be somewhat negative. Left, and I'm going to slide it through as I vary t. Overlap pictures. Meaning, as I adjust t, or as I slide t from minus infinity up to plus infinity, what's the overlap picture look like? Here's my axes, and I have f sub 1 of lambda. So here it is, f sub 1 of lambda, which was e to the minus 2 lambda. Now I need to put in the f sub 2 of t minus lambda, but I said I want to put that one in for a small enough t to where it is not going to overlap f sub 1. So here is f sub 2 of t minus lambda. Its interval of support is right there, or where the function is non-zero is between t and t minus 3. This is the first overlap picture, or first overlap pattern. And now I need to ask myself, when does this picture occur? When do I see this kind of picture where this f sub 2 of t minus lambda does not overlap f sub 1 of lambda? Under what conditions on my t is this true? So as long as this t remains to the left of 0, I'm going to have this picture, this pattern. This overlap pattern then occurs with no overlap as long as this endpoint remains to the left of 0. This overlap then is going to be true as long as t is less than 0. As long as t remains less than 0, I see this picture, and what's y of t? Y of t is the integral of the product of those two. If I multiply this times that, point for point, and they don't overlap, the argument is 0, isn't it? My output then is 0 as long as t is less than 0. Questions on that? So until t equals 0, I'm not going to have an output. And that makes sense with these two waveforms. Here's what we started with. We started with this f sub 2 that turns on at 0 and turns off at 3. And the impulse, it's a causal system, isn't it? Meaning I hit it, and it doesn't respond until I hit it. So as soon as I hit it, it will start responding. But I'm not going to hit it until t equals 0. So this is making sense. I shouldn't see an output until after t is bigger than 0. Now let me go to the next picture for overlap, and let me say this is case number 2. This is now the partial overlap picture. There's my lambda axis. Here is my f sub 1 of lambda, which is e to the minus 2 lambda. And now I'm actually varying my time t from minus infinity up to plus infinity, and part of the way through that process, I'm going to let this t go to the right of 0, and then this guy is going to remain to the left of 0. And now this is where that value of 2 is non-zero. This is now a new overlap picture. And I could have overlap even if this guy was down here. Is that clear? The overlap refers to the region where they're non-zero. It doesn't mean that this waveform is on top of this waveform. It's when they're both non-zero. This red could be negative and we would still have overlap. Is that clear? Now, there's two different things that I have to worry about. I have to worry about the interval of time when this picture is true, and I need to figure out what the result is of this overlap pattern, or I need to find the functional description. And that's going to involve the limits of my integral. So those limits of integration are going to be different than maybe the time interval when this is true. When does this overlap picture occur? So I need t to slide to the right of 0, don't I? So let me say t is greater than or equal to 0. So this pattern occurs when t is greater than or equal to 0, and we need that leftmost piece of f sub 2 to remain to the left of 0. So we need this, and we need t to be, or t minus 3, to be less than 0. And now we solve both of those for t, and we end up with t being bigger than 0 but less than 3. And that's the time interval, t, when this overlap picture is valid. So now whatever I calculate for y of t will be this value between these intervals of time t. Is it clear what I've done? I'm going to see this partial overlap pattern as long as t minus 3 remains to the left of 0 and t is to the right of 0. As soon as t minus 3 crosses over, then I have total overlap and my overlap pattern has changed. So I'm not going to look at that until I've figured this one out. Now I need to do the integral. Now I need to find the expression for y of t. Y of t is this integral of f sub 1 of lambda, which is e to the minus 2 lambda, times f sub 2 of t minus lambda, which was 2 d lambda. Now I need to figure out my limits of integration. So now is it 0 to 3? Now I need to go back and I need to, this is why it's nice to have different colored crayons. Okay? Now I need to say, if I'm integrating where these two waveforms overlap, I've now said this is the functional form for f sub 1, that's e to the minus 2 lambda. I'm multiplying that by the functional form of f sub 2 of t minus lambda, and that's just 2. But now I need to integrate that product. But where is that integration going to occur? It's going to occur from where they're both non-zero. And that's only from 0 to t. The lower limit is 0, the upper limit is t. It's not the same as when the overlap pattern is true. So I want you to be sure you're distinguishing between the overlap pattern being valid and the limits of integration. The limits of integration then are from 0 up to t. Is that clear, that distinction? So it's not 0 to 3, is it? It's 0 to t. I'm sliding t, and y of t is going to depend on what t actually is. But we'll only say that this expression is true for t between 0 and 3. But this is the expression. And sometimes on an exam, I'll just say, set up the integrals with the limits. And this is as far as you would have to take it. You wouldn't have to do the computation. But in here, let's go ahead and do the calculation. We now have 2, and then we need to integrate e to the minus 2 lambda. We have the minus 2 there, so there's the 2, e to the minus 2 lambda from 0 to t. Or we now have minus 1, and then we have e to the minus 2t minus e to the 0. Or if I distribute that minus 1 through, I now have 1, since that's what this piece was. That's just 1. So I have minus 1 times minus 1. That gives me the 1 minus e to the minus 2t. Now I know that the output response is that functional form that I just integrated over that interval of time when that overlap pattern was true. And that was when t was between 0 and 3. This was the functional form. And does this make sense? Now we say for t equal to 3, which is bigger than 5 time constants, we are, where are we? We're at 1 minus e to the minus 6. So we're basically at 1, aren't we? So our final value is going to be 1 for the output response before it shuts off. Questions on this piece? Yes? When t is 1, when t is 0, so at t equals 0, we shouldn't see anything, right? And so this convolution operation should give us a continuous waveform or response. Before t equals 0, our output was 0. Now we say, well, what's it going to be at 0? Here. We plug in 0 and we get 1 minus 1. Oh, it's 0. That's good. It's consistent. Is that okay? So now we're going to start at 0 at time t equals 0, and then we're going to build up. And this is just that exponential build formula. That's case 2 for partial overlap. Let's now do the last overlap picture for this convolution problem, which we'll call case number 3. And this one involves total overlap. There's our lambda axis. We can immediately write down or sketch e to the minus 2 lambda. That's our f sub 1 of lambda. Now we are allowing that f sub 2 to cross completely into the positive half of the time axis, or the lambda axis. Now, when does this overlap picture, when is it valid, or when is it true, or when does it occur? For what values of time is this overlap picture going to be the same? We need this guy, this endpoint of f sub 2, to slide through the origin, don't we? We need t minus 3 to exceed 0. This picture is going to be true as long as t minus 3 is greater than or equal to 0. And if we solve that for t, this overlap picture is true for t greater than or equal to 3. So t equal to infinity, this is valid. Now we need to figure out what the expression is, the y of t. Y of t is now this convolution integral. It's the integral of f sub 1 of lambda, which was e to the minus 2 lambda, times f sub 2, which was just 2 d lambda. And now what are my limits of integration? Now I have to worry about where my cross-hatching occurs. It occurs from t minus 3 up to t. And those are my limits of integration. It's not from t to infinity. It's from t minus 3 to t. Is that clear? So it's only where these two waveforms are non-zero, where they overlap, that's where we have to integrate. This is going to then be from t minus 3 up to t. Questions on that, or where that came from? And now my integral is exactly the same. It's just I have to integrate between two different limits. So if I did the integration the first time, I should be able to do it the second time. I just have to evaluate it at two different limits. In this case, I have this minus 2 over 2 e to the minus 2 lambda, but now I'm integrating from t minus 3 to t. Or this is now minus 1 times e to the minus 2t minus e to the minus 2 t minus 3. And this is true for t greater than or equal to 3. And if you wanted to clean this up or change it around a little bit, we could push the -1 through, and we have an e to the -2 times a -3, so we really have an e to the 6, e to the -2t minus e to the -2t. Or maybe that's kind of ugly, so we factor out the e to the -2t, and we have e to the 6 minus 1, which is just a number, which is a big number, but at 3, which is where this starts, it's already shrunk by e to the -6, isn't it? So we're starting at 3 at a value of e to the -6 times e to the 6, which is 1, minus e to the -6, which is where we left off in the other piece. And this is then the expression for the third case. And now we can more accurately, that's kind of loaded for me, but now we can sketch this. Now we know what it's doing functionally for all time. What is it for t less than 0? 0. Then how far are we going to, what's the largest we are going to reach as far as a magnitude? 1, isn't it? So now we can say that we are going to go to 1, and we transition around this 3. But at 3, we are actually at 1 minus e to the -6. Basically, we're at 1. So this is now going to do something like this. And what's the tail look like? Where can I stop sketching? Five tau, right? So this is going to be 5 tau beyond 3. So this point right here will be 3 plus 2.5. So at 5.5, I'm basically finished with my sketch. Should be. Meaning now I can do something like that. And that doesn't look too much different than my pulse, except the amplitude has been collapsed. Question? The question was, I only had 3 cases, and why? And it's all determined by the overlap patterns, and that's influenced by the complexity of these 2 waveforms. And so our next example, which we'll finish, we've got another 40 minutes, so we'll be able to finish that next example. It's going to be a little bit more complicated. But you could have something that was here, non-zero, and then here, and you're going to have all sorts of overlap patterns, and you'll have all sorts of cases. If we summarized what we've done for this example, we could now collapse this down and say, oh, maybe I should really summarize what we've just determined to be. And we now have y of t made up of 3 pieces, don't we? We have a piece where it's 0. That's when t is less than 0. Then we have a piece that's building up exponentially, 1 minus e to the -2t, and that's occurring between 0 and 3. And then we have a piece that's exponentially decaying, and that's going to happen for t greater than or equal to 3. And we had these 3 cases because f sub 2 had a finite duration, didn't it? And it wasn't too messy. But if we had one of those waveforms having many different pieces, then we might have a lot of different cases and a lot more lines to worry about for our expression for y of 2, or y of t. Question?
So if that F1 had been shifted into the negative axis to the left, then we could have ended up with a non-causal output y here.
Well, the question was, what happens when we start dealing with circuits? Let's say that we had something like the following. Maybe here is f sub 1 of t, and maybe it is going to be here and then here, and maybe f sub 2 of t is maybe it actually, you kick it and it maybe waits a while before it starts. Let's say that this is -4, this is -2. Let's say this is +3 and this is +5. Let's say this is 2 and this is 6. Oh boy, what do we have? Well, now we can figure out sort of when this is going to start happening or giving us results. So now you don't worry too much about causal and non-causal. You just say, oh, let's say f sub 2 is my impulse response. I now kick the system, and what happens? Nothing until 2 seconds later, and then at 2 seconds later it decides to respond, right? So now here's my input. Now, relative to this line in the sand that I'm labeling as t equals 0, I'm saying I'm going to actually start at -4. So now I hit this system at -4. When am I going to see anything happen? 2 units later, isn't it? This guy responds 2 units after he's hit. So this guy is hitting it at -4. When's the first time you're going to see anything happen? At -2. Now, we hit this guy, f sub 2, at 0. Then how long does it shake? 4 seconds. But that's 6 seconds beyond when we hit it. So now, if I say, oh, I'm going to quit hitting it at 5, when is the last time it's going to shake? 6 units beyond 5, isn't it? So at 11. So we can tell what's going to happen just by looking at endpoints. We can say, oh, -4 plus 2. Oh, it's going to start at -2, shaking. Then it may die for a while, but then it's going to kick back up. And when's it going to finally be done? When we quit hitting it and when it stops responding, which is 5 plus 6, or 11. So the output of this system would be on from -2 to 11. And that would be the interval of time that you would be focused on for this convolution problem. And your analysis should give you consistency with that just sort of mental exercise. Questions on that? I'll see you definitely Thursday. Tell your friends we have an exam, and there is an exam review tonight at 5.